want to take your highlighter and put a highlighter around this box. These are a new set of formulas that we have and we're going to be able to use, and they're on our formula sheet. And we're not going to take the time to prove these in class. If you want, you can search up on the internet and find out why is it that if you have two angles added up, does this happen? Okay? And it is not what you would expect. Most people would think this. If I had sine of 20 degrees plus x, most people think, and this is wrong, that this should be true. And it kind of makes sense that you think it should be true because you're used to distributing, right? What is the problem here? Why am I not allowed to distribute? Well, if we look back and we really dissect distributing all the way through, the only thing you're allowed to distribute is a number or a variable that represents a number. So you would be allowed to do this, right? Because the 2 out front is a number. You would be allowed to do this because the x is a variable and the x represents a number. Here, sine is a function. It is not a number. Okay? Where else can you, I'm trying to think of other functions. It used to be on computers that computers could not write square roots all the way across. Old computers, when you went to type in a square root, it would do a thing like this, and then you would have like brackets here, and have something like 16 plus 9. You know that 16 plus 9 is 25. And you know the square root of 25 is 5. So the answer to this should be 5. The square root is a function, just like sine is a function. Functions you can't distribute. Like if I tried to distribute this, and I had the square root of 16 plus the square root of 9. That's 4 plus 3. That's equal to 7. And I know my answer should be 5. But it's very easy for our brains to mix up things like, oh, this is a pattern I've seen, distribution. Well, I can distribute a number. Sine is a function. And so if you ever get two things added inside sine, cos, or tan, the only thing you can do is use these big formulas. And these big formulas are going to help us discover some important mathematics. For example, I don't know if any of you are like super structured and like things nicely, but did it bother you that on your pie plate this was 30 degrees, then the next space was smaller? Like it would be nice if it was equally spaced? Well, with these formulas you can actually add in, and we're going to add in the pi over 12 family to our unit circle. And be able to do the pi over 12 with these formulas. We can do 15 degrees, sine of 15 degrees, cos of 15 degrees without a calculator. So that'll be how these formulas are helpful. So what we're going to do is we're actually not going to do these questions in the same order. We're going to start with example 2. Because example 2 is just practice using the formulas. Oh, and on page 638, maybe we'll do that first before we get to example 2. No, that's not what I'm looking for. Example 1 here. There it is. You can put a highlighter box. There's also a formula for tangent. So we have 6 new formulas, all on your formula sheet. They're on your formula sheet. So technically, you don't have to have them memorized. But I'll tell you that you won't be able to use them unless you have them like mostly memorized. And by mostly memorized, what I want you to have in your head is if you see a fraction with a bunch of tangents, you should say, wait a minute, maybe I should look at my formula sheet. If I see cos, cos, sine, sine, or sine, cos, cos, sine, or 4 things with sine and cos, I should have it mostly memorized. I'm like, hey, maybe I should look at my formula sheet. But if you don't have it triggering you to look at your formula sheet, then you're going to miss the idea. And that's what we're going to do in example 2. So example 2 is about recognizing, hey, this looks like one of my formulas. Sine cos minus cos sine. I look on my formula sheet, and on my formula sheet I have that sine alpha minus beta fits this sine cos minus cos sine. And so when I'm looking at this, there's an alpha and there's a beta. And I'll go to my question, I'll be like, okay, so does this match up perfectly with the formula if alpha is 8x and beta is 3x? Do they have it written in exactly the same way? Do they have a sine alpha cos beta minus cos alpha sine beta? Yes. Theirs matches up perfectly. So that means I'm allowed to say that this is equal to sine alpha is 8x minus beta is 3x. This simplifies to sine of 5x. Now it still has an x. It says evaluate if possible, but there's nothing to evaluate because we have a variable. In B, I have tan plus tan over 1 minus tan tan. That's sort of how I read it. Forget about the tan plus tan over 1 minus tan tan. Is there a formula on your formulas, and I have them up on the wall over here as well. Is one of them tan plus tan over 1 minus tan tan? Looks like the tan alpha plus beta, so I'm going to write that out. I look at my formula sheet, and on my formula sheet, tan alpha plus beta is equal to tan alpha plus tan beta over 1 minus tan alpha tan beta. Perfect. So, if these are my alphas, and these are my betas, does my formula match up perfectly? Alpha, alpha, beta, beta? Yes, it matches up perfectly. So that means I can take B and I can rewrite it as tan alpha was pi over 6. Beta was pi over 12. If I wanted to add these together, I'd have to get a common denominator, right? So 2 pi over 12 plus 1 pi over 12, that'll be 3 pi over 12. 3 pi over 12 reduces to pi over 4, and that's on my pi plate. Tan of pi over 4 is 1. So this one we can actually evaluate. Circle questions 4 and 5.